For decades, engine oil thickness was treated like armor. Thicker meant safer, stronger, more protective. Before the 1990s, engines were built with looser tolerances, rougher surface finishes, and less precise manufacturing. Oil clearances were wider, combustion control was poorer. In that environment, thicker oils like 10W40 or even 20W50 weren't just common, they were necessary. When thinner oils were used in those engines, oil pressure could drop, sealing could worsen, and leaks often appeared, reinforcing the idea that thin oil simply didn't protect well enough. That historical memory never disappeared. It carried forward even as engines fundamentally changed. Fast forward to today, and modern engines are the tightest they've ever been. CNC machining, plateau honing, coated bearings, low-tension piston rings, everything is designed around precision. Yet instead of thicker oil, manufacturers are specifying oils that many people describe as water-thin. That contradiction alone fuels suspicion. When something goes wrong, viscosity becomes the first suspect, and in some cases, manufacturers themselves seem to confirm that fear by changing oil recommendations after failures become public. One of the most recent and visible examples comes from General Motors. In April 2025, GM announced a recall involving its 6.2-liter L87 V8 used in 2021 to 2024 Silverado and Sierra models. These engines were originally specified for 0W20 oil, a viscosity chosen to meet fuel economy and emissions targets. After a growing number of failures involving crankshaft and bearing damage, GM revised its guidance to 0W40. For many owners, that change looked like an admission. The logic felt obvious. Thin oil failed, thicker oil fixes it. But the recall documentation pointed to manufacturing defects, specifically crankshaft and bearing issues, rather than viscosity itself. Ford offers a quieter but equally influential case. Its 6.2-liter Boss V8 used in Super Duty trucks originally carried a 5W20 recommendation. Starting in the 2016 model year, Ford permanently upgraded the specification to 5W30. The change was framed as improved protection under heavy load. To enthusiasts, however, it looked like confirmation that the original oil was too thin. Chrysler's 6.1-liter SRT Hemi adds another layer to the story. In 2006, Chrysler issued a technical service bulletin addressing an engine whine noise at idle in several SRT-8 models. The fix wasn't a hardware change, it was a recommendation for thicker oil, often 0W40 or higher. Thicker oil reduced symptoms. Once again, viscosity appeared to be the solution. Recent peer-reviewed work shows why the debate refuses to settle. A 2024 study published in Lubricants by Lee and colleagues examined mid to low ash, low viscosity oils and their impact on three-way catalyst performance. The researchers found that lower viscosity oils increased wear risk in certain components, which could raise ash loading in catalytic converters. Yet even in those conditions, overall engine durability was not catastrophically compromised. Another 2024 study, published in Results in Surfaces and Interfaces, used modeling to analyze what happens when lubricant viscosity is reduced in the piston ring pack. The simulations showed increased asperity contact and higher friction at the ring liner interface as viscosity dropped. In engineering terms, thinner oil reduced film thickness, pushing parts closer to boundary lubrication, which causes gradual increase in wear. Yet even that narrative isn't universal. In 2025, a numerical analysis focusing on hybrid electric vehicle engines found that low-viscosity lubricants could function without inevitable damage when paired with advanced additive packages and surface treatments. The engines didn't survive because the oil was thin, they survived because chemistry and materials compensated for reduced viscosity. Protection didn't disappear, it shifted. Earlier work helps explain why these results appear contradictory. A 2021 MDPI study on lubricant degradation and contamination showed that low viscosity reduces load carrying capacity primarily when the oil is chemically degraded or contaminated. In other words, viscosity alone wasn't the trigger. Fuel dilution, oxidation, and particulate contamination were the factors that collapsed film strength and caused integrity issues. Thin oil became dangerous only after its chemistry changed. This is where the investigative question sharpens. If thin oil were inherently destructive, research would show consistent catastrophic outcomes. Instead, studies show conditional risk, trade-offs, and dependencies. That leaves a gap between public perception and scientific nuance, a gap filled with anecdotes, recalls, and fear. And that brings us to the deeper suspicion driving this debate. If thinner oils are more demanding on additives, surfaces, and manufacturing quality, why push them at all? Is the goal to protect engines for 300,000 miles or just long enough to clear warranty periods? To answer that, we have to move beyond belief and into data, used oil analysis, fleet testing, and long-term wear trends, because that's where claims meet evidence. The move towards ultra-thin engine oils didn't start with engineers chasing novelty. It started with regulators chasing numbers. In the United States, corporate average fuel economy standards don't reward big breakthroughs anymore. They reward marginal gains stacked relentlessly year after year. Automakers fight for fractions. A 0.5% improvement can mean the difference between compliance and millions in penalties. When engines, aerodynamics, and transmissions are already heavily optimized, oil becomes one of the last remaining levers. Reducing viscosity lowers the energy an engine wastes just circulating oil, and in a regulatory environment where every decimal matters, that loss becomes impossible to ignore. Inside the engine, oil is constantly being pushed, squeezed, and sheared through galleries, bearings, and tight clearances. Thicker oil resists that movement. Engineers call this pumping loss, the mechanical work required just to move oil from the sump to every lubricated surface. Thinner oil flows with less resistance, reducing viscous drag on rotating assemblies like the crankshaft and camshafts. That energy doesn't disappear. It shows up as measurable fuel economy improvement. Multiple industry studies and OEM testing programs show that switching from a traditional 5W30 to 0W20 typically delivers a 1 to 2% fuel economy gain under standardized test cycles. Dropping further to 0W16 adds another 0.5 to 1%. Those numbers sound small until you realize how difficult it is to extract even a single percent from a modern engine without redesigning it entirely. What's often overlooked is that reducing wear is, in many ways, easier than improving efficiency. Wear can be managed with chemistry, coatings, and materials. Fuel economy is constrained by physics. Once combustion efficiency and thermal losses are near their limits, friction becomes the primary enemy. That's why oil viscosity keeps getting attention. This push toward thinner oil would be reckless if engines hadn't changed alongside it, but they have. Modern engines are not scaled-down versions of 1980s designs. They're fundamentally different machines. Manufacturing tolerances are tighter by orders of magnitude. Surface finishes are smoother, and components are designed to work with thinner films. Roller cam followers replace sliding contacts, reducing dependence on oil thickness for survival. Variable valve timing systems rely on fast oil flow to actuate precisely, something thicker oils struggle with, especially at low temperatures. Honda and Toyota were among the first to build engines around these principles in the 1990s, designing oil passages, clearances, and control systems specifically for lower viscosity lubricants rather than adapting old designs to new oils. Oil chemistry evolved just as aggressively. Viscosity alone no longer defines protection. Modern formulations rely on additive systems that create sacrificial films at the microscopic level. Molybdenum compounds reduce friction by forming low shear layers on metal surfaces. ZDDP continues to protect high-pressure contact points by chemically reacting under load. Polymer viscosity modifiers allow oil to behave thin when cold and stable when hot without collapsing under shear. These additives don't eliminate the need for oil film thickness, but they compensate for reduced viscosity in critical regions. New standards like API GF7 are explicitly designed to ensure wear protection in ultra-low viscosity grades, acknowledging that thinner oils demand stronger chemistry, not weaker engines. Nowhere does thin oil's advantage become more obvious than during a cold start. This is the moment engines are most vulnerable, regardless of oil grade. Tribology studies consistently show that a majority of cumulative engine wear occurs not at full operating temperature, but in the first few seconds after startup. Industry estimates commonly place this figure around 75%. At that moment, oil has drained back into the sump, clearances are at their widest due to thermal contraction, and metal surfaces rely on whatever oil reaches them fastest. At extremely low temperatures, viscosity increases exponentially. At -30 degrees Celsius, a 0W rated oil is engineered to flow immediately under standardized cold cranking and pumping tests. A 10W oil at the same temperature can take tens of seconds to reach critical components like cam journals and valve train bearings. Some laboratory simulations and cold chamber tests showed delays approaching 45 to 60 seconds under extreme conditions. During that delay, parts are not protected by hydrodynamic films. They rely on residual boundary layers and surface coatings. Faster flow means faster film formation, and faster film formation means less metal-to-metal contact during the most damaging phase of engine operation. HTHS, high temperature, high shear viscosity. A grade like 0W20 is not a single viscosity, it is two performance targets combined into one label. The 0W describes how the oil behaves in cold conditions, specifically its ability to flow and pump during startup. Lower numbers mean easier flow at low temperatures. The 20 refers to viscosity at operating temperature, roughly 100 degrees Celsius, where the oil must still maintain enough thickness to protect moving parts. The property that bridges this gap between flow and protection is high temperature, high shear, commonly called HTHS. Unlike the standard viscosity rating, HTHS measures how oil behaves under extreme stress, similar to what occurs inside bearings and between piston rings and cylinder walls. This test is performed at high temperature and very high shear rates, replicating real engine conditions. Research across multiple SAE and industry studies shows that HTHS values above roughly 2.6 centipoise are generally sufficient to prevent excessive wear in modern gasoline engines, even when the oil's nominal grade is thin. Modern 0W20 oils are specifically engineered to stay within this protective window, resisting permanent shear breakdown that older formulations struggled with. The question is not whether the film is thinner, but whether it is thick enough for the load being carried. Engine lubrication operates across different regimes described by the Strybeck curve, which maps friction against film thickness and speed. At higher speeds and sufficient oil supply, engines operate in hydrodynamic lubrication, where an oil wedge fully separates surfaces. This wedge forms because rotating components drag oil into a converging gap, generating pressure that lifts the surfaces apart. Modern engines are designed to live in this regime. Precision CNC machining allows bearing clearances measured in microns, tighter than the width of a human hair. With these tolerances, even a thinner oil can generate enough pressure to sustain the oil wedge under normal operating conditions. The moment the engine slows, stops, or starts cold, that oil wedge collapses. This is boundary lubrication, where metal surfaces are no longer fully separated by fluid. This is where additives take over. Compounds like molybdenum dithiocarbamate, ZDDP, and boron-based additives chemically bond to metal surfaces, forming sacrificial layers that shear instead of the metal itself. In modern oils, these additives can make up as much as 30% of the formulation. The base oil may be thinner, but the protective system riding on top of it is far more sophisticated than in the past. Studies examining elastohydrodynamic film thickness show that modern 0W20 formulations can maintain protective films on the order of a few thousandths of an inch at operating temperature, enough to separate surfaces when engine design and load are matched to the oil. Peer-reviewed research from organizations like SAE, Tribology International, and major OEM research divisions provides a large body of data, and the pattern that emerges is not dramatic engine destruction, but conditional behavior tied to design intent. Across dozens of studies, thin oils consistently reduce friction and improve efficiency, while wear outcomes remain strongly dependent on engine architecture, additive chemistry, and operating conditions, rather than viscosity alone. A 2020 SAE heavy-duty diesel study evaluated a 0W30 low-viscosity oil over 100,000 kilometers. Fuel economy improvements approached 2% compared to baseline oils, and teardown inspections showed no accelerated wear in bearings, rings, or cylinder liners. Importantly, oil consumption remained stable, and wear metal accumulation followed expected trends. In a separate SAE study published in 2021, researchers pushed viscosity even further, testing an ultra-low 0W8 oil over 60,000 kilometers. Fuel savings ranged from 1 to 3% depending on duty cycle, yet ring wear, bearing condition, and cam surfaces showed no degradation relative to 0W20 when evaluated through both teardown and oil analysis. Real-world public transportation fleets tell a similar story. A 2015 study involving 39 buses running Euro 4 diesel and CNG engines compared low-viscosity oils against baseline grades over extended service intervals. Wear debris measured using ICP-AES showed iron and copper levels that were statistically indistinguishable between groups. High-temperature, high-shear viscosity remained stable throughout the intervals, and oil consumption did not increase. In a context where engines run long hours under steady load, the absence of abnormal wear challenges the idea that thinner oil automatically shortens engine life. Long-term reliability studies reinforce this pattern. An SAE investigation from 2011 examined engines run with reduced viscosity oils over nearly 200,000 kilometers. Fuel efficiency improved by roughly 1.5%, and post-test teardowns revealed piston skirts, rings, and bearings within normal wear limits. No evidence suggested accelerated degradation tied directly to lower viscosity. Similar conclusions appeared in heavy-duty truck engine tests published through SAE Mobilis, where researchers measured friction and wear at multiple engine locations using different viscosity oils. Lower viscosity reduced friction and fuel consumption, while wear varied more strongly with load and additive formulation than with viscosity grade. OEM-led research aligns closely with these findings. Honda R&D studies examining low-viscosity oils showed consistent fuel economy gains while carefully monitoring oil consumption and sliding wear at elevated temperatures. The results did not indicate inherent reliability loss, but they did highlight narrower operating margins, especially under high load and high temperature, where oil formulation becomes critical. Across more than 20 SAE papers reviewed collectively, a consistent message appears. Thin oils improve efficiency and reduce friction without producing durability loss when engines are designed for them and maintained correctly. UOA trends showed that these oils generally shear less than expected and maintain viscosity within grade for normal service intervals. Large-scale meta-analyses from communities like Bob is the Oil Guy, compiling thousands of reports, reveal that wear rates normalized per 1,000 miles remain remarkably consistent across viscosities. In Ford and GM engines, iron wear did not spike when thinner oils were used. In many cases, a sweet spot emerged, where wear remained low up to oil change intervals approaching 12,000 miles, regardless of whether the oil was a 0W20 or a thicker alternative. Blackstone's own summaries often note that thinner oils show lower initial wear, particularly in cold climates, due to faster circulation. Taken together, this body of evidence does not paint a picture of thin oil as an inherent engine killer. Instead, it shows a system that works within defined boundaries, where wear is influenced more by design compatibility, oil chemistry, operating conditions, and maintenance practices than by viscosity alone. When engines fail, viscosity is usually the easiest suspect to blame, but real-world damage almost always traces back to something far more basic: contamination. When fuel dilution from short trips or failed injectors thins the oil by 20 to 40%, or when water enters through condensation or coolant leaks, film strength collapses regardless of the label on the bottle. In these cases, wear accelerates not because the oil was thin, but because it was no longer oil in the chemical sense it was designed to be. That focus on the number overlooks a deeper reality the research keeps returning to. Additive chemistry often matters more than viscosity itself. As far back as classic SAE Mobilis papers, bearing wear was shown to correlate more strongly with anti-wear and friction modifier packages than with oil thickness alone. Modern oils rely on complex interactions between ZDDP, molybdenum compounds, boron dispersants, and polymer viscosity modifiers to form protective boundary films when hydrodynamic lubrication breaks down. Two oils with the same viscosity grade can produce very different wear results if their additive systems differ, which explains why many thin synthetics outperform thicker conventional oils in used oil analysis despite having lower nominal viscosity. Honda, Toyota, Ford, and others now mandate 0W20, 0W16, and even lower viscosities across millions of vehicles globally, and their internal durability testing and field data show no epidemic of wear-related failures tied to oil thickness. API and ILSAC categories, including FA4 for diesel engines, explicitly allow thinner oils with reduced film thickness, while requiring stricter wear protection, oxidation control, and shear stability. Fleet operators running low-viscosity oils across thousands of trucks report consistent fuel economy gains of 1 to 2% over millions of miles. Still, the data does not say thicker oils are never useful. Under severe high-load and high-temperature conditions, such as towing, track use, or sustained high RPM, lab and engine tests show thicker oils can reduce wear by roughly 5 to 10% by maintaining stronger hydrodynamic films. Aging engines with worn clearances often benefit from higher viscosity, with used oil analysis frequently showing reduced consumption and more stable oil pressure after stepping up a grade. The data-driven takeaway is straightforward. Follow the manufacturer's specification, not folklore. If there is doubt, used oil analysis offers a direct window into what's actually happening inside your engine.